Okay, welcome everyone. Tony, could you just check if the, you are checking. Is there some sound coming through there?
Yeah, you got audio.
All right, excellent. Check if the, you are checking. Is there some sound coming through there?
Yep. You can tell the lag. Come in 4 or 5 seconds.
All right, welcome everyone. So today our fourth lecture on probability distributions and applications. This lecture kind of ties up what you've been doing so far, and it's the perfect place after which to have an exam because we have a set of sort of self-consistent stuff here. I'll explain what I mean. So what are the main things that you have, I won't say that you've learned, but that we've covered so far in this course? We started with different types of data, right? Categorical, nominal, yeah, ordinal, continuous, yeah. And then we kind of shifted gears into probability, and that seemed kind of disjointed from what we had done the first couple classes. We did probability, we did Bayes' rule, some logic notation, and today we bring it all together because we're going to talk about probability distributions for different types of data. So we'll be going back to binary variables and continuous variables and talking about probability distributions for them. So there's a method to the order that we've had things in so far because you need to have some coverage or view of data types and of probability in order to understand probability distributions. So I'm going to go briefly over again properties of probability that we covered and then introduce to you the normal distribution and the binomial distribution from chapter 3 in your textbook. And then I'll have some time at the end to do some discussion and Q&A about the exam. Recall mutually exclusive events. These are things that cannot both be true. Only at most one or the other can be true, such as having cancer or not having cancer. And recall how we represented these as a non-overlapping Venn diagram. And the probability of the union of these two events, so for example, of having cancer or not having cancer, is just equal to the simple sum of those two probabilities. And if those are also exhaustive, there's no third possibility, then that sum has to equal 1, because the sum of probabilities of all possible events always equals 1. And conversely, the probability of having cancer and intersected with not having cancer is equal to 0, since these are exclusive events. For non-exclusive events, these are things that can both be true at the same time. There is an overlap in this Venn diagram. And this overlap area is the intersection, or the and of the two events. So as an example, having cancer and having heart disease, these are not exclusive events. It is possible to have both. And then the equations for the union and the intersection are a little bit more complicated. The probability of having cancer or heart disease is equal to your probability of having cancer plus your probability of having heart disease minus the probability of both cancer and heart disease, because then otherwise we're double counting this area here. And the probability of both, the intersection, is equal to the product of these two if they are independent. If they are not independent, that is to say that the probability of having cancer, given that you have heart disease, is not the same thing as just the probability of having cancer, then we need to reflect that conditional probability of one or the other of these in this equation. Any questions so far? And you may recall that from this third equation is where we derived Bayes' rule from, just by the property of commutativity, that the probability of A and B is the same thing as the probability of B and A. And so these two, the two events have to be interchangeable, and that is where Bayes' rule comes from. A little reminder of your cheat sheet, what all of these things mean, just for going forward and solving problems. I won't go over all of this again, just to remind you that especially important is this idea of conditional probability, which is the probability of an event here A conditional on B being true or B having happened. And that is something different than the joint probability, which is the probability of both things being true. We also talked about marginal probability, which is the probabilities that we wrote in the margins of the table, or the probability of A independently of whether or not B is true. So there was our quick review of probability notation and properties of probability, and I think we can now move on to random variables. Starting with the definition of a random variable, which is any characteristic that can be measured or categorized, and where any particular observation or outcome is determined at least partially by chance. So it can be mostly predetermined or not at all predetermined, but at least some component is due to chance. For example, the number of new cases of diabetes in New York City in a given year, you can imagine some component of that is deterministic, and you could predict it from year to year based on previous years and maybe on your knowledge of things like the population of the city and changes in exposure or things like this. But at least part of this is going to be determined by chance. You can't know exactly what this numbers will be in a given year. Or the weight of a randomly selected individual, also a random variable. So the important thing about both of these things is that it is something that is measurable. And if you measure it, you will observe a particular outcome. But until you measure it, there are a range of possible outcomes that you might observe. And this is what makes it a random variable. And I'll break these down in the same way that we broke them down before. Categorical, which includes nominal. Discrete random variables, these were the things that you count, like number of children, and continuous random variables, which is where those any value is possible between your bounds. And I also included ordinal random variables in the categorical category. Some notation to try to keep things clear. I will write random variables in uppercase Roman letters and particular realizations of the random variable in the corresponding lowercase Roman letters. So for a random variable X, like the number of cases of diabetes in New York City in a year, x lowercase x1, x2. These could be the cases in certain given years, the actual realization or observation of the random variable. So the blood groups, this is an example of a categorical random variable where in, oh, sorry, I gave the answer away, but in the population, these are the percentages or the prevalences of each of the blood groups. So in advance, you can know that someone is most likely to be an O positive, but in any group of people or for any individual, you don't know what that is until you observe it, which is what makes it a random variable. Or the number of visits to the obstetrician's office during an uncomplicated pregnancy. I won't give the answer to this kind. What kind of random variable is this? Discrete. Yeah. Very good. It's 0, 1, 2, 3. It can't be anything in between these values. This is certainly a discrete random variable. And quantitative. How about the distribution of BMI in a population? Quantitative. Yeah, it's quantitative. Yes. And that's because it's a ratio of height to weight and decimal places. And even if our height and weight are measured on as integers, in theory, it could lie anywhere between the bounds of the possible. So let's talk about continuous random variables to start out with. And what is the probability of a continuous random variable? If we visualize it, it's a curve with all of the allowed values of that random variable on the x-axis and the probabilities of each of those on the y-axis. So here's a couple examples of a fairly symmetric looking bell-shaped, maybe normal distribution here, and of a skewed distribution here. And I'm going to just note here that in these distributions, it's not so much the value at any given point that we're interested, but it's going to be the area under this curve over some interval that is of interest. So in this case, the shaded area here will be interpreted as the probability of this random variable taking a value between the lower end of the interval and the upper end of the interval. And in the second plot, we've shaded an area that is the probability of an observation of this random variable taking a value of 45 or anything greater. So it's the cumulative probability of a range of possible values. That's something that'll is a bit different than with categorical variables. So we're interested in intervals along this curve. These intervals must have a cumulative probability of somewhere between 0 and 1. Will in general be 0 if that interval becomes infinitesimally small, and 1 if it covers the entire range of allowable values. The two most important probability distributions for this class are the normal distribution that we will begin in starting in November. We will start using the normal distribution for hypothesis testing, and the binomial distribution, which is what we're going to use for binary outcomes. But by the end of today, we won't be doing hypothesis testing, but should be able to, before the exam, be able to make calculations of probabilities using these distributions. I'll show you how to do that during the rest of the lecture today. So let's talk about the normal distribution. This is for a continuous variable. It is symmetric and bell-shaped and characterized by two parameters, the mean and the standard deviation. You recall I use Greek letters when I'm referring to a population parameter. This is the mean mu in the population and the standard deviation sigma. This, of course, doesn't always have to be population parameters, but in this case, I'm talking about the population, and you know that because I'm using Greek letters. The normal distribution, by the way, turns out to be an extremely fundamental distribution. And it's really interesting, the range of situations where the normal distribution comes up as being relative. Essentially, any time that you have an observation that fluctuates due to random errors, no matter what the distribution of those errors are, if you have a number of independent errors adding together, you get a normal distribution. It's super general. So it comes up, in physics, it comes up in public health, it comes up in biology, because it arises from such a fundamental process of having a series of random events that add up to give you some uncertainty. Here's an example of 3 normal distributions. Four. And they demonstrate these 2 different parameters. So we have 3 of them here that have the same mean mu that are all 0. So that is the center of the distribution and the point about which it is symmetric. But these 3 differ in their standard deviation, the second parameter. That second parameter determines the variance, or standard deviation, or the spread of the data. So this first one is sigma squared, the variance of 0.2. The second one, this is variance of 1, and then this third one is a variance of 5. So the larger the variance, the more spread out this becomes, and the narrower it is, the more steep and tall it is. And then this final one, the sort of outlier, differs both in the variance, which is 0.5, and in the mean, which is -2. So this one is symmetric, about -2. So here's a real example. The mean and standard deviation of heights of women are approximately 65 inches with a standard deviation of 3.5. With men, the mean is a bit higher and the standard deviation is a bit higher as well. So you see that reflected in these 2 normal distributions. So you have a fair bit of overlap here, but still some difference in these distributions. And when we get back to hypothesis testing, you will find out that a lot of essentially the hypothesis testing that we do in this course has to do with inference about whether the observations you have are consistent with a single distribution, or whether that's implausible and you think they must have come from 2 different distributions. So here, within what interval do almost all of the men's heights fall? So that's this one. I guess about 60 to 80. So with the center being at 70, they almost all fall within plus or minus 10 inches, which is about 2.5 standard deviations. And for the women's, it's between 55 and 75. So that's again plus or minus 10, again more or less plus or minus 2 standard deviations. Well, turns out there's a pretty handy rule of thumb called the empirical rule that applies to any normal curve. If something is normally distributed, then within 1 standard deviation of the mean will contain 68% of your probability, or in a large sample, 68% of your observations. Within plus or minus 2 standard deviations, that's 95% of your observations, and within plus or minus 3, 99.7% probability. So this is just kind of a handy thing to have in the back of your head, this empirical rule. You don't need it. You can look these up. You'll be learning how to look things up in a table or calculate them with software. But when something is an integer number of standard deviations, you can tell these probabilities right away. So for example, from the empirical rule applied to the heights of adult women, where the mean was 65 and the standard deviation was 3.5 inches, the plus or minus 1 standard deviation is 61.5 to 68.5, or 65 plus or minus 3.5. That's 68% of women will have heights in this range, 95% between 65 plus or minus twice the standard deviation, and 99.7 between 65 plus or minus 3 times 3.5. Oops, I got it. Yeah, that's right. So this is a range 10.5. This is almost plus or minus, almost plus or a range of 2 feet. So that is indeed, you expect, given a range of 2 feet, it should contain almost everyone's heights. So here's a question a little bit trickier, but where you can still use the empirical rule. What proportion of women are less than 68.5 inches tall? So that's the mean plus 1 standard deviation, but no longer looking at a symmetric interval. And I'm going to give you lots of these little kinds of questions, and they will certainly be well represented on the test as well, just seeing that you can calculate probabilities along some interval of a random distribution. The reason for that is that this becomes the basis of all of your hypothesis testing. And in order to understand the inferences that you are making in hypothesis testing and in confidence intervals, you have to be comfortable with these random distributions and calculating probabilities along intervals of them. So who's got an answer? Looks right to me. 68 plus 16 equals 84. Very good. Okay, so there's the normal distribution can have any mean and any standard deviation, but there is one special normal distribution called the standard normal distribution. And this is the one that has a mean of 0 and a standard deviation of 1. That's the standard normal distribution. And any normal distribution, if you take all of its measurements, all of the possible values, so this x, capital X being a random variable that is a normal distribution, if you subtract the population mean and divide by the population standard deviation, this returns to you the standard normal distribution with mean 0 and standard deviation 1. When we convert individual observations using this equation, those are called z-scores. And capital Z is normally used to represent the standard normal distribution. It's worth noting that the standard normal distribution looks exactly the same as any other normal distribution, except for the scale on the y-axis and the location on the x-axis. That's because all it is a shift to 0. So here are some heart rates with a mean of 60. You're just shifting the mean to 0, and then you're dividing by the standard deviation so that that standard deviation is 1. The shape is exactly the same. There's only one shape of a normal distribution. Why we care about a standard normal distribution? It's really a convenience. It makes it easier to compute probabilities, and you can do it with a table of probabilities. And it's something that you can also sort of do calculations on the normal distribution in your head, thinking of variability in terms of numbers of standard deviations from the mean. So in your textbook, Appendix B.1 is what they call the normal probability table. And this is a picture taken from the textbook. What it gives you is the probability in the left-hand tail of the standard normal distribution. So it's giving you areas that look like this. For a negative value of z, something like this that is less than 0.5, and for a positive z, it's something like this, and a probability greater than 0.5. They only give you the left-hand probabilities because you don't need the right-hand tail probabilities, because of this property of probability that the probability of all possible outcomes must sum to 1. So if you look up the left tail distribution for this particular value and you find that it's 0.6664, then 1 minus that has to give you the remainder of the area, that which is right on the right tail. So that's why they only give you the left tail probabilities. Some tables go even further by, for example, only giving you, if it's left tail, only giving you the negative z, or if it's right tail, only giving you the positive z. Because similarly, if you wanted to calculate this probability for positive z, you could do it by taking the corresponding negative value, probability for the corresponding negative value, and subtracting that probability from 1. Oh, this is small. Okay, maybe see it a little bit better here. So here's a little exercise. Find the probability that a normal random variable takes a value of less than 1.5 3 standard deviations above the mean. So quickly, do you expect this to be more or less than 0.5?
More.
Sorry?
More.
More, yeah, it's going to be more than 0.5 because it's above the mean and a left tail distribution. It's going to look something like this. So pulling out this table, so 1.43 standard deviations above mu. The way the table works is in the rows, you have up to 1 decimal place, and in the columns, you have the 2nd decimal place. So to look up 1.43, we go down to 1.4, and go 0, 1, 2, 3. It's 0.9236. So your probability of an observation that is 1.43 standard deviations above the mean or less than that is 92.36%. Indeed it is. How about the probability that the variable takes a value greater than the mean plus 1.43 sigma? It's just 1 minus this. Because again, like we were covering, these are they're mutually exclusive and they are exhaustive. So 1 minus 0.9236 gives us the answer. These are some important C values, but I would say the only one that you really need to know is this one. This is going to come up over and over again. That the probability of a random variable that is standard normal taking a value greater than 1.96 is 0.025. The probability of the absolute value, so meaning either greater than 1.96 or less than minus 1.96, what's that going to be? 0.05 or 5%. Yeah. Yeah, so that comes up over and over because we will talk later about the p-value, which turns out to be the area under the tails of a curve. And we'll talk about the confidence interval, which is the area in the middle of the curve. And 0.05 is a common threshold for p-values that we use, and the 95% confidence interval is a common confidence interval. And if it is for something that is from a standard normal distribution, then 1.96 is the critical value. A little hint, you can use the table, and that's fine. You can also use the norm.dist function in Excel. There's also a p-norm and a q-norm function in R, and I'm not sure how you do this. I don't know if you can, Tony, just ask for the probability for a value of z in SPSS, but certainly you can do it in Excel, and this is not a bad way to check your work. Look in the table and do it in Excel and make sure you get the same answer for your exam. You can probably tell by all the problems that I'm giving here that these are good questions for the exam, calculating probabilities. In this case, I'm just doing it in terms of means and standard deviations, but certainly you can get questions about all kinds of potentially real-life variables. So how do you do this? Find the probability that a normal random variable assumes a value within 1.43 standard deviations of the mean. Well, this is the area in between an interval. You can calculate this, and there's multiple ways to do it. One way is to take the probability of z less than 1.43, so that would be everything to the left of here, and then subtract this, everything to the left of here. That's what I've written out here. The probability of z less than 1.43 minus the probability of z less than minus 1.43. Or alternatively, the probability of z greater than minus 1.43, that would be everything to the right of here, minus the probability of z greater than 1.43. That is what you would use if you had right tail probabilities. It's the values that we looked up before and turns out to be 0.8472. Another way you could do this would be to start with 100%, subtract this left tail, and double that, because we know that the area up in the right tail is the same by this symmetric property. You get the same answer. So I have a suggestion for you that when you're given a problem that is written out in text, to actually go ahead and draw the normal curve and shade the area that you're calculating. It'll help you not to make mistakes when you're doing it. And it's even not a bad idea when you're doing hypothesis testing, so that especially if you are doing when we get to what is called one-tailed hypothesis testing. It can get a little bit confusing, but it helps if you draw out the interval of probabilities corresponding to the probability that you're calculating. All right, well, here's a couple more example questions. I think I'll skip past these, but just to give you an idea of a few more that if you want to have the answer to. So those were questions about, for a given value of z, what's the probability? What about the reverse question? For a certain cumulative probability, what is the value of z? So in this case, you're given the probability, you need to find the value of z. And to do this, you just use that same table in reverse. You just look for that probability in the table and read the corresponding z-score. In software, it's a so-called quantile function. If you look at that norm.dist function in Excel, there's an option for whether you want the quantile or the probability. In R, it's Q norm for quantile and P norm for probability. An example of this kind of reverse lookup: what is the value of z for a cumulative probability of 0.025? This magic value that came up before, not really magic, but say special. You look for a cumulative probability of 0.025 in that table and find that it corresponds to this special value of z minus 1.96. Similarly, what's the value of z for a cumulative probability of 0.975? Well, you have the full range of lookups, like our table. You can just look up 0.975. If you only had the values for half of the table, you could go 1 minus this to get 0.025. see that corresponded to minus 1.96, and use the symmetry property to know that that the value where less, or where 97.5% of the probability lies, is positive 1.96. And if these are not just z scores, the first thing if we're doing a quantile calculation, you will look up the z-score, and then you'll have to convert that in reverse back to the original scale using the standard deviation. And so here's a nice step-by-step process for solving all of these kinds of problems that involve the random normal distribution, and that will also apply to other distributions that you'll learn. There will be other ones, but you can use the same approach. But first, state the problem in terms of capital X, the random variable, and lowercase x, the realization of the random variable, such as the probability of capital X, so the probability for the random variable being less than this particular realization, lowercase x. Then standardize your random variable to restate the problem in terms of the standard normal distribution. So this same statement is equivalent to saying it's the probability of capital Z being less than lowercase x minus mu over sigma. And you draw a picture so that you know which interval you're calculating the probability for, and then go to your table or the software. Second major random distribution. These aren't the only two, they're just the most important ones. We will cover at least also the t-distribution this semester. But the binomial distribution is the other most important one. So whereas the normal distribution provides probabilities for a continuous variable, binomial distribution provides probabilities for a binary variable, such as having cancer or not having cancer. Now, for one realization, for an individual having cancer or not having cancer, that is one realization. What does the probability distribution correspond to? Well, it's the probability of a number of events in a group of individuals or a group of observations. For example, what is the probability that among 100 randomly selected individuals, 60 have private health insurance? So given 100 observations, the binomial distribution is going to give us the distribution of probabilities for different numbers of events in that sample size. Now, the binomial distribution is also a pretty fundamental distribution. That's because it's quite broadly applicable, again, under just a few assumptions. The first one, that a trial or an observation has only two possible outcomes, which we will call a success and a failure. Even if they're not really successes and failures, normally you pick one of the possibilities to be what you call a success. Each trial or each observation has the same probability of success. So those 100, in order for the total count to beat up binomial distribution, every one of them has to have the same probability of the success outcome and the failure outcome. And finally, those N trials have to be independent. So they are independent observations. This is an assumption that we make over and over, the assumption of independence. So this means that if you observe 3 successes in a row, it doesn't mean that your 4th has any greater or lower chance of success, because they're independent from each other. The order of the observation does not matter. Yes?
Is that different than the point before that each of them have the same probability of success?
Yes. Because, so by probability of success, trying to think of actually in what situation you could have them all having the same probability of success, but them not being dependent. I mean, before you started your trial, you could devise something where you say every outcome has the same probability of success, but it's a conditional probability. So it's conditional on the outcome of the previous trial. That is one case where you could say sort of a priori they have the same probability of success, but it's dependent on the previous observation.
So does it refer more to order than sort of success?
Yeah, I think of this third one, the independence one, as meaning that the order is irrelevant, that you can have your, if I have, if my trial consists of everyone in this room, it makes no difference in what order I observe everyone. This, by the way, has a name. It's called a Bernoulli trial. If something satisfies these 3 assumptions, then you call that a Bernoulli trial.
A what?
A Bernoulli trial. It's one where also the number of observations is determined in advance. So if I say I'm going to make 100 observations, those observations obey these 3 rules, and that's called a Bernoulli trial. The Bernoulli trial, its number of successes follows the binomial distribution, which is this, where exclamation point is factorial. Factorial being defined for integers, it's that number times the number minus 1 times the number minus 2 down to 1. Quick trivia question, who knows what the factorial of 0 is? One. It's 1. This binomial distribution actually looks, so it is a probability distribution. Forget why I said looks like. I really should say it is. It is a probability for each number of successes x out of n trials where each has a probability of success p. Here's 3 different binomial distributions. For, in red here, is n equals 20 and a probability of 0.5. What's the most probable number of successes? N equals 20, probability of success is 0.5. Sorry? Why? Well, so n is 20. Let's say this is, since it's 0.5, we'll think of this as a coin flip. I'm going to flip a coin 20 times. And I'm going to call a success being heads. What's the most likely number of heads if I flip a coin 20 times? Yeah, 10. Yeah, so you see here at 10, 10 is the most likely probability, but it's not the only probability. In fact, any number of heads between 0 and 20 is possible. This binomial distribution gives me the probability of each number of successes, given that n and that p. The second one is in green, n equals 100. Probability is 0.5. What's the most likely number of successes? 50. 50, very good. Getting quicker here. And the third one, the blue, n equals 100 and a probability of 0.3. What's the most likely outcome? Little trickier. Yep. 30. That's right. So n equals 100, probability of 0.3. 100 times 0.3 is 30. And that is the most likely number of successes to observe this Bernoulli trial. Yes.
Those we can call normally distributed.
Good observation. They sure look normally distributed, don't they? Yeah. In fact, for reasonably large n and n times 1 minus, sorry, reasonably large NP and n times 1 minus p, that is where neither tail here is, or where the lower tail is not too close to 0, the binomial distribution looks very much like a normal distribution. And we'll use that approximation. Anytime you have a fairly large n and the lower tail doesn't get too close to 0, the normal approximation to the binomial distribution is very good. Good observation. All right, here's an example. If the prevalence of diabetes in an elderly population is 10%, then what is the probability when you randomly select 4 individuals from this population that exactly 3 of them are diabetic? So what are my assumptions here in order to make this calculation? Yep.
Your assumption is that at least 3 of them are going to be diabetic.
That's not an assumption, that's the question.
But 3 of them are going to be chosen? Randomly selected?
No, we're selecting 4. Yep.
That each time you select a person, it's independent of the other.
Yep. So when's a case when that might be violated? What's that? Sure. If you were actually selecting them from the same family, then that assumption might be violated, because if one of them has diabetes, then maybe it's more likely that the others do as well. But if we're selecting them from the wide population, then that assumption is probably good. What are the other assumptions?
There's 2 possible outcomes, that they're either diabetic or not diabetic.
Mm-hmm.
And that there's the same probability of success.
Yep.
So the same probability that they'll choose each one.
That what?
Is it the same probability that they'll choose each one? Or, oh no, the same probability that a person could get diabetes.
Yep. So we have to make the assumption that everyone has the same probability of diabetes of 10%. Yep.
Would that be the distinction between same probability of success and independent? That independent means each person in the population has the same possibility to be chosen, and probability of success out of those chosen is equal.
Well, you could choose from the population without everyone having the same probability of being chosen. For example, you could, if you had a, this is a common thing to do, but if there's a minority group in your population that with uniform sampling, there would be too small of a sample size to study, you can oversample the minority population in order to have a sufficient sample size of the groups as well, and undersample a majority group of the population, and still have those three assumptions be valid, that they're independent, those probabilities are independent, that the probabilities are the same for each one, and that there's the two outcomes. So the probability that exactly 3 of them are diabetic, that is this probability of x equal to 3 for the binomial distribution with n equal to 4 and p equal to 0.1. And you can plug that into the formula on the previous page, or you can use a calculator that we will give you. I think it's up on Blackboard already, the binomial distribution formula that just has that formula already programmed into it. And it turns out this probability is pretty small, 0.0036. And it's only a 10% probability that one person has diabetes, that a particular person has diabetes. So for 3 out of 4 of them to have diabetes, the probability of that is pretty small. So if I saw this, I would think either we got just pretty lucky or unlucky to find 3 out of 4 people with diabetes, or I would think that maybe those the assumptions of this calculation are incorrect, either because those observations weren't independent of each other, or because maybe that you've selected people for which the probability is not actually 10%. So from the same population, and again 4 individuals, what's the probability that at most 1 will be diabetic? So you can calculate that from the probability for x equals 0 plus the probability of x equals 1. That's pretty high, 95%. Uh-oh, my equation didn't, or my answer didn't come out here, but what is the probability that if you randomly select select 4 again, that at least 1 of them will be diabetic? So you could do this as probability x equals 2. Oh, this is hard. Plus, you just tell me so I don't have to write all this out. miss one. We also need probability of x equals 1. Then there's one more, right? What's a shortcut I could have done here? Save some calculation. What's up?
Probably of 9. 1 minus 1.
Yeah, 1 minus probability of none having diabetes. Oh, that would be easier.
What did you just write then?
What's up?
What did you write? Last one.
1 minus the probability of x equals 0. So you can use that spreadsheet calculator, or you can just use this binom.list function in Excel. It's pretty handy. Basically, you give it x and n, and it calculates its probabilities for you. And I think it also has options for whether you just want to calculate it for this particular x or a cumulative probability for anything at that value of x or less. As you guessed, the binomial distribution can be approximated by a normal distribution with a mean of n times p. That's how we noticed that the middle of it was the number of trials times the probability of success in each trial. And a standard deviation is the square root of n times p times 1 minus p. So with this mean and standard deviation, you can approximate the binomial distribution pretty well. I think I wrote, assuming that that left tail is not too close to 0. And I give a rule of thumb in a couple of slides about that. So this comes in really handy when we're talking about large samples, like 1,000 individuals. At this point, doing the exact calculation would be really problematic because you'd have to take a factorial of 1,000, which probably causes an error in your computer. So if you try to do this in Excel, I believe it will just automatically use an approximation because you can't calculate a factorial of 1,000, and because that normal approximation is very good for such a large sample. So with that prevalence of diabetes equal to 0.1, then we expect about 10 of them to have diabetes, yes?
So does that mean if we have a large sample and a very small probability of success, we can't really?
Yeah, so for a very large sample and a very small probability of success, eventually you will learn to use the Poisson distribution in that case. But this is, yeah, this might be getting into Poisson territory here because it's only an expected number of 10. Basically, yeah, for small expected values here, especially if this were like 1, 2, 3, that would be a Poisson distribution. For somewhat larger values, the Poisson distribution again becomes a normal distribution. So what's the standard deviation here? It was the square root of 1,000 times 0.01 times 0.99. So that's about the square root of 10, or about, I guess, 3.3. So 10 plus with a mean of 10 with a standard deviation of 3.3. So the mean minus 3 standard deviations is 0, so it's not too close to 0. It's still going to be a pretty good approximation. So I say this here works well if NP and N1 minus P are both at least 15. That's certainly true, but that's very conservative. The example on the last page, N times P was only 10, but I think it's still going to be a pretty good approximation. But if they're at least 15, it would be even better. I actually think the better rule of thumb is that if there are not expected to be any observations, or a very small fraction of observations that would be less than 0, then it's a good approximation. As we know, in a Bernoulli trial or something like that, you can't observe a negative number of successes. It has to be 0 or more, which is why this approximation kind of breaks down if the distribution gets too close to 0. So in this example here, with the prevalence of 0.01, yep.
Well, I was going to ask, could you repeat if there's a small number of cases that are less than 0, you said?
A small probability that is less than 0. If the area of the normal approximation that is negative is negligible, then it's going to be a reasonably good approximation. Another thing I'll note about approximations is that in general, approximations to a distribution become less good out near in the extremes of the tails. So that's a shortcoming of these rules of thumb, and there are rules of thumb like for the t-distribution and other things too. But in general, when you're looking at the middle of the distribution, these approximations are quite good, and the further you get out on the tails, the less good they are. So if you want to calculate the probability in the tails that contain 0.01% of the probability, then that approximation is going to be less good for the same distribution as your approximation of like the middle 50% or even the middle 95%. Because it's out at the tails that differences between the binomial distribution and the normal distribution become more pronounced. So in this example here for a binomial distribution, if we were asking for the probability of an observation between 5 and 8 using the normal distribution, you would just add up those 4 probabilities. Whereas for the normal approximation, everything in between, not just the integers, has a probability, so you have to calculate the probability along the interval as we practiced for the normal distribution. And we would take halfway between the integers, so go from 4.5 to 8.5 instead of just 5, 6, 7, 8. All right, to wrap up, the probability notation that we've learned and the ability to make calculations of probability. These are key things that you've learned so far. You're going to use the normal distribution, the binomial distribution, normal approximation to the binomial distribution, and especially probability calculations throughout the rest of the course. Remember these new notations, the difference between a capital X and a lowercase x. The capital is the random variable, the lowercase is the realization of the random variable. N being a sample size, P a probability, mu the population mean, sigma the population standard deviation, Z a very particular, geez, that's my Canadian background coming out again. I thought I was so good at saying Z now. Z, Z, this letter being the standard normal distribution. You should be good and comfortable with probability calculations and looking up, either calculating or looking these up in a table for these two distributions, and making calculations for the upper and lower tails and various intervals along the normal distribution. With that, just a little bit late, I'm going to wrap up the lecture, but take some time for you to ask any questions that you might have about the exam. The exam covers these first 4 sections up to and including today. Anything that is in these lectures is fair game, and anything that is in the assignments.
What's the format?
So the format, you will come in here. You can use your own laptop or one of the room computers. It is an open book exam. You can bring anything that you want into the exam, except for a friend and except for access to a friend. So I'll expect you to use only the materials that you bring in. I also expect you not to be accessing new materials and looking things up on Google or posting things on a message board or anything like this, using materials that you bring into the exam. So you're free to bring your textbook, lecture notes, any other notes that you have taken, and you can bring in, for example, the probability distribution calculators, the binomial calculator that I've given you. Essentially, bring in what you think you need for the exam, including everything that we have covered and any additional materials that you think would help you. So it's an open book exam, which is a blessing and a curse. It's a blessing because I'm not going to test your memory. It's a curse because I have to come up with some other ways to test your comprehension of the materials.
So there's going to be like a mixture of like open-ended questions and multiple choice.
Yeah, a mixture of open-ended and multiple choice. It's mostly multiple choice. There will be a couple open-ended questions, but I will warn you, and so I don't actually know what's going to be on the exam yet. I'll figure it out before next Monday.
An hour before.
An hour before, maybe a little bit before, but I do. It has been noted to me in previous semesters that the first exam is tougher than the homeworks have been. The homeworks are kind of practice in that, but I do try to take you a little bit outside of your comfort zone and test your comprehension and your ability to apply the things that you've learned. So there will certainly be a fair bit of just doing, again, more of the same calculations that you've been doing. But I'll try to throw some things at you that look a little bit unfamiliar, but they are still testing the same concepts. Nothing out of left field. It's all really using the things that you've learned in these 4 lectures. But certainly with some of them, trying to test your critical thinking and application of the concepts.
Is there a question for SPSS?
Yeah, there will be some questions where not specifically SPSS, but where you should produce some plot or will have to use your software to do something.
How long is the exam?
Sorry?
How long is the exam? 2 hours?
Yeah, it's the full length of the class, so you'll have like 2 hours and 50 minutes. I don't like putting a lot of time pressure on you, so my intention is that it will be an exam that if you're a fairly quick exam writer, you'll probably be done it in under an hour. But with the 2 hours, 15 minutes, you should have time to take your time to go back, check everything, to work your way through the questions without racing against the clock. Okay. Yep.
Slide prior to this one.
Yep.
We're gonna do after the lab now.
Yeah, you'll have some examples of doing this in the lab now. Yeah, this is making an exact calculation from the binomial distribution and then repeating it with a normal approximation, and you'll get practice working with the normal and the binomial distribution. Normal approximation. Yeah.
And the binomial distribution is for discrete values.
For when there are two outcomes, binary values.
Okay.
So the number of successes is a discrete outcome. So yeah, in that sense, the distribution it's a discrete distribution. It's quantitative in that those are real numbers and they take only integer values. So yeah, the binomial distribution is the distribution of a discrete random variable.
One more question.
Yeah.
Will we be getting feedback like on the homeworks to know like if we're on the right before the exam, like to know if we're like in the right direction or making things up or
so actually this question came up yesterday because apparently there was I checked the syllabus had a due date of next Monday, but that's
exam
date.
Yeah, I kind of disclosed it a little earlier because of it. But yeah, I changed the due date, but I encourage you to do it before because.
yeah, but the question is, will we be getting feedback to know like if we were doing the right things in the homeworks before the exam?
What is the feedback?
Yeah, on assignment 1, it should be graded. I mean, all these submissions should be graded. Assignment 2 grades automatically.
Oh yeah.
Okay.
So I'll take a look. Thank you.
And you can always eat it. I really encourage you to use the discussions forum. If you have a question about a particular problem or something you learned in class, you post it in the discussions forum, give a more detailed answer, and everybody can. Not only that, but other students can contribute to that as well. So it really helps if you use that. If you send an email and I just respond to you, then you're going with it.
Has anyone managed to install the Blackboard app on their phone or tablet? No. I installed it on my phone, but I haven't been able to use it to actually access the discussion board. As soon as I open it, it gives me an error.
Yeah, IT has to enable that.
Oh, okay.
I think that's really what the problem is that the ISID that that the main campus hasn't really enabled it for mobile access.
Yeah. So it's really annoying because I don't get any kind of notifications that there's been a message. I just have to go and check Blackboard on my desktop or laptop to see. But great. All right.
Thank you.
I have a question about practice questions. Practice exam or practice questions.
What's that?
I have a question online about whether it might be Some practice questions.
Some practice questions. That's a good question. Yeah, I could find some practice questions.
We have some canned stuff.
Yeah. Yeah. Okay, I'll try to get some additional practice questions to you, say by tomorrow.